Is it a good morning or not?
Yeah.
Yeah? It's okay? You're just quiet. I have a feeling like yesterday and today, I woke up and I didn't want to be awake. I can't tell you what I'd rather be doing because I'd rather be doing nothing. Right? It's not like there was something else I wanted to do instead. It's just I just didn't want to be. So, yeah, I get it. But one foot in front of the other. I knew you guys would all be counting on me, so thank you for dragging me out of bed.
You're welcome.
We need to finish up whatever chapter we're on.
11.
Thank you. Glad somebody knows where we are. And then get started on the next two chapters, which are kind of a combined chapter. When we get there, I'll explain what's going on there. But let's finish up fluids and then get into some temperatures and some thermodynamics and that kind of stuff. We had just finished with the siphon using Bernoulli's equation to calculate the speed of fluids in pipes, that sort of thing. But what I want to demonstrate for you and talk with you about now is something called Bernoulli's principle. Now, this is kind of the conceptual thing that follows as a consequence of Bernoulli's equation. And it's a weird one. It kind of goes against your intuition, but I'll show you that it's true nonetheless. The faster a fluid moves, the lower its internal pressure. So we tend to think of pressure as like, okay, so for example, if I went and grabbed a garden hose and I started squirting you with water, right? You'd be mad at me. It'd be cold, it'd be unpleasant, but you'd be mad. If I went and instead got a fire hose, okay, not only would you be mad, you'd be injured. Why? Why is the fire hose so much worse? The pressure, right? There's more pressure in the fire hose. So we tend to think of pressure as like what's hitting us. And that's not really, I mean, pressure can be that, but the pressure we're talking about in fluid dynamics is the pressure that is internal to the flow of the fluid. The pressure of us being hit by water, that's more like conservation of momentum problem. We're talking about the pressure that exists inside of a fluid as it moves from one point in a pipe to another. Now, this fluid doesn't have to be in a pipe. It could be the fluid that is racing over the wings of an airplane. It could be the fluid that's inside of your blood vessels right now. It can be the fluid that's outside your car as you drive down the freeway. Wherever there is a moving fluid, that motion causes a lowering of the internal pressure. And so now I need to prove it to you, and then we'll do some calculations. You can do this experiment at home. Okay, you can take two pieces of paper, and what you want to do is you want to hold those pieces of paper like kind of as close to each other vertically as you can, kind of like this. What I like to do is I like to kind of pinch it between my fingers, and then I take my thumbs and I kind of just steady how I hold it with my thumbs behind it, right? And then just bring it so that they're about an inch apart from each other, okay? And then hold them in such a way so that you can make it possible for you to blow between the pages. It's subtle. What happens if I blow between the pages? Do you see how they get squeezed together? That's Bernoulli's principle. The faster a fluid moves, the lower the internal pressure. Where was the low pressure? Inside or outside the piece of paper? Inside, because that's where the fast-moving fluid was. Higher pressure outside, so the pieces of paper get squished together. Let me show you the correct way to use a leaf blower. Okay, leaf blowers push air really fast, right? Ostensibly, you're supposed to blow off the walkways or whatever with it, right? No. It's going to be loud. I can't talk while it happens, so just observe. I have the Force.
So you're a Jedi.
Yes, right? What the heck was going on there? Why was the ball hovering? Midichlorians. Where was the fast-moving fluid?
The air.
But where was it?
Around the ball?
It was around the ball, right? So there was this fast-moving stream of air around the ball, and the low pressure was where the ball was. The ball always went to the low pressure zone. So much so that even if I tilted it, gravity couldn't win, right? Now, eventually, if I tilted it far enough, gravity would have won, okay? But this ball was able to stay floating in that stream of fast-moving fluid because the fast-moving fluid had a lower internal pressure. So airplanes fly because of this. The air over the top of the wings moves faster than the air below the wings because of the wing's shape. And that faster moving fluid over the top has lower pressure than the slower moving air below, and the net pressure is upwards, which gives the plane its lift. So let's do a similar, I think you have a homework problem where you're asked to do a plane, airplane wing, but I'm going to do this as a window in a high-rise building, because this is something that engineers actually have to design around, okay? Because if the air blows fast enough, you can actually pop windows out of their casings. So what's going on here, right? What we're going to do is I'm going to draw a picture where we have this is like a side view, right? So there's a big window and a big high-rise kind of thing. This is not to scale. But there's like an inside and an outside, right? And outside this building, we have air, right, flowing around at 11.2 meters per second. It's probably not flowing away from the building. It's probably flowing across the window. 11.2 meters per second, that's what was that, 45 miles an hour, something like that? Okay, so pretty steady wind here, right? It's not like hurricane force. And they gave us the dimensions of the window, right? The window itself, okay, is 4 meters one way and 1.5 meters the other way, okay? And we want to find out how much force is acting on this window simply because the air is moving across it. How fast is the air moving on the inside of the building? Yeah, it's 0, okay? And then V outside, right, is 11.2 meters per second. So which way will the force be? Where is the lower pressure? Inside or outside? Outside. Why is the low pressure outside? That's where it's moving, right? The faster a fluid moves, the lower its internal pressure. And so the low pressure's on the outside, the high pressure's on the inside, or higher pressure's on the inside. So which way will the net force be? Does force go from high to low or low to high pressure? It goes from high to low. So the net force is going to be outwards. We're going to find out what that net force is by finding this pressure difference. The way we're going to do it is by taking advantage of Bernoulli's equation, if I can actually get the numbers in the right spots. One with 1s on it, and then ones with 2s on it. PV2 squared plus rho GH2. Okay, so we apply this like we do it with conservation of energy. We need an in and or out, a 1 or a 2, a final and initial. We need 2 points of comparison and a 0 point for height. So where's the 0 point for height going to be? Yeah, it can be where the guy's standing or anywhere actually. We'll go ahead and put it there, right? Doesn't matter because what is H1 and H2? Yeah, they're the same. This window doesn't change levels, right? So if H1 and H2 are the same, that means that no matter what those numbers happen to be, those two terms are going to cancel each other out. It's the density of air. We're on the same planet. Two terms equal on either side of the equal sign. Cancel each other out. Okay, so what does that leave us? That leaves us, let's do, what do I have in my notes? Let's do P, let's see. I need some labels. Let's make this one P1. Let's make this one P2, right? So I'm going to solve for P1 minus P2, the pressure difference inside to outside, right? So if I do that, I move the P2 over. That got a negative sign on it, right? If I move the 1/2 rho V1 over to the other side, it picks up a minus sign. And so my delta P, the difference in pressure across this window, is 1/2 times the density of what? What's the fluid that's moving? Air. Okay. And then V2 squared minus V1 squared. So that's what we're going to go calculate. And I think I did that somewhere. I got 81.5 pascals, I think. Yeah. Okay. That's the pressure difference across the window, inside to outside. If atmospheric pressure were on the inside of the building, 1.01 times 10 to the minus 5 pascals, right? We would subtract 81.5 to find out what the pressure is outside the building. But what we have is the pressure difference inside to outside, which is kind of what we want because this is what's going to give rise to our net force. What now is go back to the beginning of this chapter. What's the relationship between pressure and force? Anybody remember what pressure? Yeah, it's force divided by area, right? So if we're going to find the force, we're going to take the pressure and we're going to multiply by the area. Do we know the area? Yeah. It's 4 times 1.5, right? It's a rectangle. So the pressure is 81.5 pascals. That's a SI unit, so we're safe. And then this is going to be 4 times 1.5 in meters, so that would be square meters, right? And because we're using SI units, we're guaranteed that this will come out in newtons. And when I do that, I get 489 newtons of outwards force, okay? So 489 newtons. A newton is about 1/4 pound. This is about 500 newtons. So what's 500 divided by 4? It's 50, okay? No, 500 divided by 4 is 775. No. 250, what's 250 divided by 2? 125, we would get there in the end. 125 pounds of force on this window. So what does that mean, like the civil engineer had to design for? What is the thing that holds the window in place? How much weight does it need to support? Not just the weight of the window itself, but the outward pressure that's caused by a 45-mile-an-hour wind blowing around it. What if we doubled it and brought it up to 80 miles an hour, which is a hurricane force wind? Excuse me. Anything over 75 is hurricane force winds, right? So I did the quick calculation. Just doubling the velocity gets us almost 2,000 newtons of force out. That's over 500 pounds of force acting on that window. And so this is what they design high-rises to be able to withstand. Okay? In New York and other places that have large skyscrapers that go for a couple, 3 city blocks, and they basically, it's like a concrete canyon, a steel and concrete canyon. The air moving through there, because of the equation of continuity, air flowing in a big space that's forced to go through a narrow opening will speed up. It speeds up and routinely can be 75, 80, 90 miles an hour between the skyscrapers, even though the wind speed elsewhere is only 30 miles an hour. So they design these buildings and these windows to be able to handle this, but it doesn't stop them from popping out every once in a while and causing some mischief, so to speak. But the whole point here is the faster a fluid moves, the lower its internal pressure. All right, that was the end of chapter whatever that was. What was it, Brandon? 11? So moving on into thermodynamics proper. Let's see. Today we have tomorrow. Tomorrow there's going to be a lecture and kind of graspy things. I moved the homework, right? Please tell me I moved the homework. I remember doing that. Okay, good. So homework is due tomorrow, so there'll be time tomorrow. I'll do a little bit of lecture, and then there'll be plenty of time to finish up your homework, get it done. I'll be there to help you, all that kind of stuff, right? And then Thursday we'll continue. Next week, we only meet on Tuesday. We are not meeting on Wednesday. Why are we not meeting on Wednesday?
You're sick.
Because I'm going to be sick. Your other teachers might not be sick. I'm not responsible for them, okay? But for my campus is open, other classes are happening, but my class will not be happening, which means you might have a better day. So we have today, we have Thursday, we have Tuesday. When we come back from Thanksgiving, what are we doing that Tuesday? Review for the exam that's going to happen on Thursday. So we're going to have Tuesday and Wednesday to kind of get ready. So that really means the last lecture is next Tuesday. I have like 3 total lectures. So tomorrow I'm going to use up a little bit of the time to lecture with. Okay? So, but to cut some corners on thermodynamics because we're running out of time by design and because I don't like it, chapter 13 is concept only. And I will cover all the concepts you need to know in lecture. So yeah, I know you guys don't read the book anyway, but like, don't worry about any of the math in chapter 13. Okay, so chapter 12 and 13 kind of together. I want you to turn to your neighbor and, I keep forgetting, bring your quiz sheets on Thursdays. Thursday, I'm going to tell you how to turn in your quiz sheets. There'll be other days to turn it in, but just if you can remember to bring them on, if you don't have them already, I'll tell you how to turn them in. Turn to your neighbor right now. It's not a quiz. Turn to your neighbor and give like the difference between these things. Like tell them what it is and how they're different from each other. Go. What?
Professor Kawagoa says physicists are dumb because SI units are very inconvenient. She said chemistry.
Only inconvenient for people that work with small stuff.
I think she said something like, who cares about the scale of the universe when all we care about is like us?
Of course she would say that, yes. But my argument is that CGS doesn't care about us. Meters and kilograms cares about us. It's kind of awkward to measure ourselves in grams.
What did she say? She said that she would never measure the distance from Greeley to Fresno City College in meters, but she would measure it in kilometers.
Yeah. But a chemist wouldn't. A chemist would use centimeters.
Oh, you're right.
Yeah. All right. What's temperature? Speed molecules move out. You're way ahead. Okay. If you've been in chemistry, sort of.
Measurement of the average.
Okay. Measurement of the average what?
Energy.
Energy in something. Okay. Which doesn't tell us much of anything, right? Because if we asked everybody in this room, what's the temperature of the air in this room, right? There's approximately 52 of you in here, right? There would probably be like 56 answers, right? Just knowing humans, right? Okay. I love my wife. I love poking fun at her. She's not here to defend herself. So I always refer to her as my finely calibrated lady because she's comfortable between 72 and 75 degrees Fahrenheit. Yeah. If below 72, she's too cold. Above 75, she's too hot. She's finely calibrated. right? Whereas like as soon as it gets over like 65, I'm like, oh, it's hot, I can't stand it, right? Okay, so different people have different tolerances. And temperature is one of those things that like humans are really bad at measuring, like guessing, right? We need devices that can tell us what the measurement is. But the measurement is a measurement of the average energy per molecule in whatever it is you're sampling, which doesn't kind of help. But it does tell us the difference between what temperature is and what thermal energy is. What's thermal energy? Don't use the H word. Thermal energy is the total. Okay? Temperature is a measure of the average energy per molecule. But thermal energy is the total amount of energy something has in it because of all the wiggling and jiggling that the molecules are doing. Which of these, okay, so two beakers sitting on the same stove. Which of these has a higher temperature? One on the left, one on the right. One on the left has a higher temperature. How can you tell? The thermometer is reading higher, right? So on average, the beaker on the left has molecules with more energy. But which of these two has more total energy in it? Probably the one on the right. Why is there more total? There's a lot more molecules, right? Each of those molecules on average has energy less than the molecules on the left-hand side, but there's more of them. Think about it this way. If you had a hot cup of coffee and an Olympic-sized swimming pool that was frozen solid, which of those has higher temperature? The coffee, right? But which of them has more thermal energy? The pool, because the pool has more total energy in it, even though each of the molecules in that pool has lower energy than, say, a molecule in the coffee. So thermal energy is all about totals and can be difficult to come figure out. But temperature is all about averages. So that leaves the third thing, heat. What's heat? Give you a hint, it's not thermal energy.
Does it have to do with heat tax?
No? Eh? What did your chemistry teachers tell you it was? No? You didn't learn about specific heat capacity? Yeah. What's heat?
The amount of energy you can store.
No, that's thermal energy. Heat is energy transferred. Heat is energy in motion. Heat is what you do to move energy around. And we are going to study something called heat transfer mechanisms, which to me is just redundant. It's like the Departments of Redundancy department, right? It's like heat transfer means energy transfer, right? Unfortunately, even in physics, but especially in chemistry, so we are guilty of this as well, and you will hear me say it because it's kind of what we've sort of standardized around. You might hear me talk about the heat that is contained in a substance, the heat in an ice cube, the heat in a cup of water. Technically, that would be thermal energy, okay? Because heat is what happens when you transfer energy between things, okay? So just trying to be careful there and also realizing that heat gets a bad rap because we use it for a lot of different things, right? All right. What sort of fight is going on here? Or more appropriately, what the heck happened to Fahrenheit? Stupid. Yes, why is it so stupid? Well, sure it has a basis. Yeah, but have you ever heard you know what an idiom is? It's like a saying or a phrase that carries meaning, right? There's an idiom that in the United States that too many cooks spoil the broth. Like when you get too many cooks in the kitchen, you spoil the dish. What is that trying to tell us? Too many people with opinions on how to cook something, all putting ingredients in can cause the whole dish to taste bad. The reason I'm talking about this is because that's what happened to the Fahrenheit scale. Okay? Fahrenheit was trying to develop a scale that could be used to measure like human body temperature, and then the scale got co-opted to do weather phenomenon, and it just got weird after that. Okay? So the Fahrenheit, it's stupid. It's just dumb. It's what we're used to here in the United States of America because we just measure everything in Fahrenheit, but it's not what we actually standardize. We standardize, of course, on Celsius, even here in the United States. What's the difference between Celsius and Fahrenheit? We're arguing over what? Yeah, where's zero, right? So where does Celsius put it? Puts it, the freezing point of water is 0 on the Celsius scale. And then to get to the boiling point of water, because it's a metric scale, you just do 100 divisions, right? How many divisions are there here? I think this is 180. Is this 180?
Yeah.
Sure. It's whatever 212 divided minus 32 is. Okay? 180 divisions. I mean, I guess in some sense it gives you a little bit more like precision. But what degree is bigger? A Fahrenheit degree or a Celsius degree? Celsius by a long shot, right? Yeah, almost double the amount of temperature change in a Celsius degree. So going from like 25 to 26 Celsius is almost like a 4.5 degree change on the Fahrenheit scale. Unfortunately, to convert between the two scales, you can't use a conversion factor. You have to use a conversion equation. I don't do it that way. I just write these down and forget about it. So to get from Celsius to Fahrenheit, you use that one. Whatever 9/5 times the temperature in Celsius is, add 32, you got the temperature in Fahrenheit. To go the other way, you do that. Sorry, there's just no easy way to go about doing this, other than just asking Google or ChatGPT. Well, don't ask ChatGPT; they'll be wrong. But just asking Google, asking Siri, right? They'll just use their internal calculators and they'll tell you what the difference is. Or it used to be in the old days, you just went to the bank. Because banks took it upon themselves for some reason to tell you the temperature, the weather, and then the temperature in both Fahrenheit and Celsius. The little bank signs would switch between Fahrenheit and Celsius for whatever reason. What's going on with the Kelvin temperature scale? It's arguing about where 0 is, right? That's what makes the Kelvin temperature scale perfect. Okay? Celsius is okay for humans. But if you're really going to put 0 in the right place, you should put it where the lowest temperature in the universe is. So what's the lowest? I'm not sure I can conceive of a highest temperature. Is there like a temperature that's so hot it doesn't matter anymore? Well, yeah, right? But like lowest temperature. What happens at the lowest possible temperature in the universe? That's wrong. That's what your chemistry teachers will tell you, but that's not true. Because everything's always jiggling all the time. I don't know why chemistry teachers have this compulsion to run to everything stops wiggling at absolute 0, okay? Because quantum mechanically speaking, nothing's wiggling anyway. It's a bad argument, okay? That's because chemists tend to think of like molecules as springs, and it's a good lie. It's a good lie. They should run with it because they can do a lot of really good stuff in the world with it. But chemists have the perfect definition for absolute zero already. And they just ignore it. And I don't know why they ignore it. What happens to a gas? Let's just use a gas. What happens to a gas when you heat it up? Like what happens to the volume of the gas, its density? Like what happens when you heat up gases? They expand, don't they? Their volume gets bigger. Okay. What happens to gases when you cool them off? It gets smaller, right? So you heat a gas up, it gets more volume. If you cool a gas down, it gets less volume, right? What's the lowest temperature you can achieve? It's when the volume of the gas becomes what? Zero. Assuming we don't liquefy the gases or do any of that kind of stuff, then the lowest possible temperature one can achieve in the universe is when a gas obtains zero volume. That's what absolute zero is defined as. So, is it possible for a gas to take up no volume? No. No, you cannot take a gas which consists of atoms that have mass, electrons and protons and all, right? All that stuff takes up volume. So it is impossible to achieve absolute zero in our universe. We can get close. We're down to billionths of a degree above absolute zero. But you can never quite get that zero volume with something that has mass and volume itself, right? But the idea of what absolute zero is, it's the temperature that an ideal gas would have a volume of zero. Okay? That simple. I don't know why we need to bring quantum mechanics into it, because we don't. All right. So that's temperature scales. You should be able to convert back and forth between temperature scales. Watch out. Some problems, I can't remember if I assigned you one or not. They'll ask about like what the temperature difference on one scale is to another, right? They're not asking you to convert, say, from 18 degrees Celsius into Fahrenheit. They might say a temperature difference of 18 degrees. That's a delta, right? It's not the actual temperature. So just be wary of the language sometimes. They try to make these conversion problems harder than they need to be. And they really don't need to be that hard. What happens to anything if you heat it up? We just talked about this. It expands, right? And if it cools off, it contracts. This is what you might see on any bridge, anywhere as you're driving along. That little zigzaggy thing right there is called an expansion joint. What's it for? Has nothing to do with the number 42, I promise.
It's when the bridge expands and contracts.
Right, okay. Why would the bridge expand and contract? Temperature changes. What are bridges made out of? Stuff. What kind of stuff? Concrete and metal. What's the ground made out of?
Stuff.
Not concrete and metal. So the rate at which the ground changes its shape based on temperature and the rate at which concrete and steel change their shape according to temperature are different. So you need to have allowances built into the road surface where the bridge connects so that it can expand and contract without breaking or buckling the road. There are cracks in the sidewalk. I'm not talking about the ones that are there because of the tree roots. I'm talking about the ones that they put in there on purpose, right? And you play that game as a kid, step on the crack and you fall and break your back, whatever, right? Okay. Why do those cracks exist? Expansion joints, right? If you didn't do that, if you just poured a slab of concrete, say in the summertime, and then in the wintertime it got colder, it would literally crack itself apart as it tried to change its shape because of the temperature, okay? This is a picture. So these were train tracks that were laid, I think in China somewhere. They came up with this ingenious idea that instead of putting down the tracks in segments, okay, that they would put them down as a long continuous pour of molten metal that would just solidify as they went along, okay? Now, that works, believe it or not, we take sections of rail here in the United States, and as they lay the rail down, they actually weld the pieces of rail together with thermite. So our rails are also big, long, continuous things of metal. It's just that we connect them to railroad ties with big nails and pins and things like that. That keeps them from changing their shape with temperature. Okay? In this particular area, they weren't careful. They didn't have any ties down, and the temperature changed before they were able to really kind of set the thing. And because the temperature changed and the metal didn't have anywhere to go as it tried to expand, it expanded sideways and bent the train tracks. Okay? So kind of a clever idea that they had sort of tried to plan around, but then in execution failed, and you got the wiggly lines. This isn't going to be a quiz, but let me cue up the video. The case here is one of how does thermal expansion work, and how does it work in terms of a hole in a piece of metal. And show it. There we go. Work? Come on.
This thin brass plate has a circular hole in its center. When the plate is heated, will the brass expand inward? Will the hole become bigger, become smaller, or remain the same size?
Okay, no quiz. Just turn to each other. If they heat that brass plate up, does the hole in this inside get bigger, smaller, or stay the same size? Go. Remember that things expand when they heat up. All right, commit to one of the three answers. Everybody needs to vote. Okay, how many of you say the hole gets smaller as the brass expands? How many of you say it stays the same size? How many of you say it gets bigger? Oh, okay, so bigger one slightly, just slightly. Let's see what happens.
To verify our result, we compare the size of the hole with the size of this ball, which will not quite fit through the hole. We now heat the plate.
So exciting, right? Thermodynamics is so exciting. This actually takes like 5 or 6 minutes.
After the plate is heated, the ball fits through the hole, indicating that the hole expands when the plate is heated.
So why does it expand? Shouldn't expansion mean that everything expands and so the hole gets smaller? That's usually what people guess. Why does the hole get bigger? What is thermal expansion? Every dimension has to expand, including the circumference of the circle. The space between atoms has to get bigger, which means that the circumference of the circle has to get bigger. Yeah. Okay. That's what thermal expansion means. Okay. So it's not that it gets bigger and causes the hole to be smaller, because that would be a reduction in circumference, which means all of those atoms and molecules would get pushed closer together. That's not what happens. So there is one material that disobeys this rule of thermal expansion, of as you make it hotter, it expands, and as you make it colder, it contracts. What's the one material? Water. Okay? And it's a good thing that water does this, right? Water is its most dense at 4 degrees Celsius. At 4 degrees Celsius, it is not yet a solid. So, regardless of whether or not a lake is frozen over, I can tell you exactly what the temperature is at the bottom of it during the winter. What's the temperature at the bottom of the lake going to be? 4 degrees Celsius. How do I know that? It's water at its most dense. Greater density means it's going to sink to the bottom. And water, the temperature at which water is its most dense is 4 degrees. So the water at the bottom, this is great for our biology and evolution as we know it on this planet today, because if water froze from the bottom up, like if water was like everything else, right? Oceans and lakes, everything would freeze from the bottom up, which would make the kind of evolution you and I depend on really difficult. Okay? So part of the reason you exist is because water breaks the rules. As water freezes, it actually starts taking up less space. So this is why ice floats on the top of water. So you just kind of have to keep in your head, okay, water is kind of funky. It's most dense at 4 degrees. If I cool it down more than that, it's actually going to start expanding again. And then we get to this topic. I hate this topic. I'm not supposed to say that in front of students. This topic is so fun. This is a couple of packets of, I think, German chewing gum. And do you notice what units they're using on the packaging? There's calories, calorien, right? Also equals a number of kilojoules. Heat and calorimetry are all about keeping track of where energy is going or how much energy it takes to pull off certain things. And the units that we use in physics are, of course, joules, right? Because that's the unit of energy. Unfortunately, historically, and to this day in chemistry, calories are used, okay, as a unit to describe what's going on. Does anybody know what a calorie is? No. What? Oh, you're so close. So close. No. Okay, so the definition, the official definition of the calorie is the amount of energy it takes to change the temperature of 1 gram of water 1 degree Celsius from 14.7 to 15.7 degrees. I didn't make that up. Not my fault. Okay? So, what is a calorie? It's an amount of energy, right? Just think of it that way, right? The calorie is how much energy you need to change 1 gram of water 1 degree Celsius. How much is a gram of water? It's a cubic centimeter. Basically like a sugar cube sized amount of water. Okay?
Is that big C calorie or little?
Yeah, okay, good. Right? So I had a student many years ago email me this picture while she was on vacation. She was so thrilled. She had gone down to Mexico, and she was thrilled to see, okay, that her can of coconut water had both. It's really kind of weird, right? Notice though on the top box, kilojoules and kilocalories. In the United States, if you look at a food label, it'll tell you how many calories there are per serving. Okay? Oh, do you have one?
Yeah.
What does it say?
200 calories per serving.
200 calories per serving, and it's serving one bar?
One package.
One package? Okay, so there's whatever, were there like 2 or 3 in there? Okay, 2 bars in there. So you said 200 calories? 200 calories per serving in that package. That is a capital C calorie. That's a dietary calorie. A dietary calorie is 1,000 normal scientific calories. Okay? So notice on this can, they're being considerate and accurate in saying kilocalories up there at the top, right? A kilocalorie is a dietary calorie. So if Brandon's bar there had 200 dietary calories in it, how many actual calories is that? Try again.
20,000.
Try again.
200,000.
200,000 calories. Feeling okay, man?
Yeah.
You can be able, okay, all right. 200,000 calories. The amount of energy required to heat 1 gram of water, 1 degree Celsius. 200,000 in that bar right there, right? When you jump on the treadmill or whatever and you burn, it says 100 calories, which by the way is pretty much of a lie because it doesn't know very much about you. That is a dietary calorie. How much energy has actually been expended? 100,000 scientific calories. Why do dietitians do this? Why are food labels written in capital C calories? It's just fewer zeros to carry around. And you know, people would freak out, especially here in the United States, if you walked around and said, well, you need about 18 million calories per day, right? Like they'd be like, huh, right? Okay. Was it 1,800 calories, like kind of average for if you're exercising and not pregnant and not trying to lose weight or whatever, right? Okay. It's all different for everybody now. It used to be everybody was the same and it was 2,000, but that didn't work. So 2,000 with another, 2 million, right? So 1.8 million. This can does us a service by telling us, right, kilocalories and the joules, because joules is the actual unit of energy, right? But then they come down here at the, what just happened? 24 kilocalories, 73 kilocalories per can, and then all of a sudden 73 calories per can? What calorie are they talking about? The dietary calorie. It just, once again, units are a problem the world over. We should just all go metric and not argue about it anymore. To get between a calorie and a joule, where do I want to put it? We'll put it right here. 1 calorie is equal to 4.186 joules. Okay. So you can convert real easy between joules and calories. It's not that big a deal. The bottom line is a scientific calorie. The bottom line is a calorie is a unit of energy. It's an old-fashioned unit of energy that chemists still hold on to, but pretty much everybody else has moved over to joules. Unless you live in the United States and you try to go buy an air conditioner or a heater, and then they'll tell you that the heater or air conditioner puts out BTUs, or the British thermal unit. British thermal unit is the amount of energy it takes to take 1 pound of water for 1 degree Fahrenheit, I got it written down here. 1 pound of water through 1 degree Fahrenheit from 63 to 64 degrees Fahrenheit. Why are the definitions so picky on what temperature you use? What does water do? When you change the temperature of water, what happens to its density? It alters, right? So the definitions are very particular about what temperatures you do this at. But yeah, just watch out, right? The generally accepted, although this isn't like in the documentation, a capital C calorie is 1,000 lowercase calories. Lowercase calories are generally reserved for science, and dietitians will use the capital C calorie. Although I've noticed the new generation of dietitians are starting to use kilocalories as their unit, which is good. All right. The table you see here is something called specific heat capacity. And specific heat capacities crop up when we try to measure the amount of energy that's required to change the temperature of a material. The amount of energy Q is proportional to the amount of temperature change, delta T, And that proportionality is the mass, how much material you have, times a constant for different materials. It's that little c there that's called the specific heat capacity. Okay? Now, this is something, again, that my students that have chemistry before kind of come out of chemistry a little bit shell-shocked about. They're never quite sure like what specific heat capacity is. It's got a terrible name. That word capacity on the end leads your brain to think what? Like how much it holds. This has nothing to do with how much it holds. Okay? This has everything to do with how much energy it takes to change the temperature of something. So I'm going to use an analogy that we use in physics all the time to describe what this is that we've tried to teach the chemists and the chemists have never caught on to. Okay? I think it's because they're afraid of physics. But we've already learned an identical idea, and that identical idea is inertia. Thermal inertia is specific heat capacity. The specific heat capacity tells you how much a material will resist changing its temperature. The higher the specific heat capacity, the more energy it takes to change the temperature of that material. So if we look at this table, what's like the winner on this table? Which one of these has the highest specific heat capacity? Water. 4,190 joules, right, per kilogram Kelvin, right? Kind of a funky unit, but the unit works out. But that high number tells us that water has the largest thermal inertia of all the things on this table. Meaning it requires a lot more energy to change its temperature. Compare that to copper. 390, 0.39 times 10 to the 3, right? 390 joules per kilogram Kelvin. That is a lower number, which means that copper will change its temperature much faster than water ever would. So let's talk about cooking for just a little bit, okay? And what is the best material for cooking on? The answer is, it depends. What kind of cooking are you trying to do? If I'm going to be sautéing something, a sauté is a method where you use high heat to get a quick sear or color, usually onto vegetables. Searing for meat, coloring for vegetables. So if I'm going to sauté some mushrooms, okay, I'm going to put a little bit of fat in the pan. The fat is there not just for flavor, but to allow better thermal conductivity between the food and the pan. But to sauté correctly, I need the pan to heat up quickly, and I need it to cool down quickly. I need to have very precise control over the temperature, because if it goes too high, I end up burning things. If it goes too low, I end up boiling things. Dish no good. Okay? Especially if like a stir fry. A stir fry isn't a sauté. A stir fry is a special technique that requires rapid changes in heat in order to get correct. And so in order to have rapid change in heat, what kind of material do I want? Do I want it to have a high specific heat capacity or a low specific heat capacity? I want it to be low. Remember, it's like thermal inertia, right? The lower this number, the faster it will respond to energy inputs. And so things like copper are really good. The problem with copper is that it's a very soft metal. If you try to cook with copper pots, you end up bending them and kind of breaking them and poking holes in them. And so you need alloys of copper, or even better, pans that are they're like different materials put together. So you can see this one has a copper core with some aluminum in it and then some stainless steel. Stainless steel is fantastic. It's like bomb-proof, okay? We can see here that iron is 0.47, so it's kind of close to copper. The aluminum at 0.91 or 910, right? The aluminum can hold on to a little bit of heat. Right? So you kind of, in these multiple ply pots and pans, you kind of get the best of both worlds. You can get them to go fast, but you can also kind of get them to retain their heat if you want. I also have a picture on here of some of my favorite cooking material, which is the cast iron pan. It's a little bit harder to get a sauté right in a cast iron pan, not impossible. But with cast iron, you can do things like braises or deep frying. These are things where you want the pot to hold on to its heat and you have a consistent amount of heat going into the food. And cast iron, being thick and massive and made of iron, can pull that off, okay? Things you don't want to make your pans out of: mercury, lead, salt, beryllium. Okay? Do not boil your pasta in ethylene glycol. Okay? That's antifreeze, by the way. Okay? So what we're going to do is we are going to try to use our newfound knowledge of what sort of temperature changes and heats and all that kind of thing are. And we're going to attempt to figure out, right? We can figure out just about anything, but usually we're looking for the specific heat capacity of something, right? Some unknown material, like as in this example right here, okay? We're going to find the specific heat of the sample. Again, those of you that are coming out of chemistry, I don't know why chemists do it the way they do it. Did your classes, I love chemists, I just don't like chemistry, okay? And I don't blame your chemistry teachers because this is how they were taught and are continue to be taught in the books and stuff like that. Did your chemistry teachers do something like Q hot equals minus Q cold? Okay. We're not doing that. Okay? Because it's horrible. It's horrible for a lot of reasons. And one of the reasons is that minus sign that they have there. Okay? This is physics, right? Why learn something new when we can just use old stuff? Something from a toolbox we already have. Okay? And the toolbox we're going to use is conservation of energy. Because that's what calorimetry problems are. They're conservation of energy problems. Whatever the changes in heat are, you just add up all the changes in heat, you're going to have to add those up to 0. In a calorimetry problem, we assume that all the parts of the problem are isolated from the rest of the universe, that there's no input energy or output energy. Whatever energy gets transferred between, say, hot water and cold pasta or whatever, the pan, right? It's all internal to the system. Okay, we're not going to handle, not yet, we're not going to handle like burners on a stove or anything like that. Okay, so in any calorimetry problem, what are we adding everything up to? 0. And it's important that you remember we are going to add everything up. You're like, but Mr. Balogh, what about the minus cold one? Don't go there. Don't confuse the issue. What are we doing? We're adding. That's all we're going to do. This is a sum. Okay? And what does the sum add up to? 0. Okay? I'll write the 0 first, just because I like getting it out of the way. Okay? In this problem, how many materials are there? How many masses are there? I see a sample of metal. I see a copper cup and water. Right? Those are 3. If you want to draw a picture, here's your copper cup. Here's your water. Here's your metal sample. Okay? There's 3 things here, right? Okay? So, I'm going to write down 3 Qs. Q metal plus Q copper cup plus Q water. Do you see how we're just adding them all together? That's all we're doing. Have we figured out which one's hot and which one's cold and which one's minus and which? No. We're just going to add them all together. But Mr. Balogh, how's this going to work? You can't add 3 things together and get 0. You can as long as one of them is negative. Which one? Don't care. Don't care. I don't care. Why don't I care? Because the temperatures cannot lie. Which of these things, the water, the cup, or the metal, is cooling off? The metal. It's going to start at, what did we say, 100? Okay? And it's going to drop down to something. The water and the cup are going to go from their initial temperature up to something, right? Okay. As a matter of fact, we know what it is, right? 25. Okay? So the metal went from 100 to 25. It cooled off, right? So in the chemistry method, you'd have to play around and put that on the minus side and figure all that out. Watch. Watch the beauty of just adding things together. What are each of these Q's? M, mass of what? The metal. Specific heat of the metal, delta T of the metal. Right, MC delta T for everything. Okay. Plus mass of the copper, specific heat of the copper, delta T of the copper. Plus mass of the water, specific heat of the water, delta T of the water. See, add them all up. Add them. Don't think about it. What's the mass of the metal? 100 grams. What are you going to do with that? Convert to kilograms. Okay. What's the specific heat of the metal? 370. No idea. Okay. Don't know what it is. So I'll leave it as a symbol. Okay. What's the change in temperature of the metal? What's the final temperature of the metal? 373. Nope. 25. What was the initial temperature of the metal? 100. Celsius? Oh, we can use Celsius here? As a matter of fact, we can. Because a Celsius degree and a Kelvin degree are exactly the same thing. All right? Plus mass of the copper. What's the mass of the copper? 0.075. It's 75 grams, right? Divided by 1,000. Specific heat of copper. I know this. 387 in SI units. Technically on this table over here, okay, 0.39, I went and looked it up a little bit more exactly, okay. That's 390 because it's 0.39 times 10 to the 3. Notice the units right here, joules, kilograms times degree Kelvin. We're not using the calorie gram Kelvin, which you probably used in chemistry, okay. We don't have to change our temperatures into Kelvin because we're doing a temperature difference. And a temperature difference, a delta, on the Celsius scale and the Kelvin scale are identical. There's 100 degrees between freezing and boiling on both scales. They just argue about where to put 0. Add 273.15 to any Celsius temperature and you get Kelvin. Okay, so we're going to use 387 in SI units. I'm not going to put the units in. As long as I put in kilograms and I put in joules per kilogram Kelvin and I do temperature in Celsius, I'm going to be okay. All right, what's the change in temperature of the copper? What's the final temperature of the copper?
25.
What's the initial temperature of the copper? 20. Plus mass of the water. 0.15. 4,186. I got that one memorized because I always use it. And then water starts at, ends at 25, starts at 20. Okay. What is this right here? A number. What is this right here? Another number. Good luck in your TI calculators getting those numbers correct. Suggest you use something else, okay? Or be very careful with your parentheses, right? But the point is those are just numbers, right? Okay? But Mr. Balogh, they're all adding. What are you doing? The chemistry teacher's going to kill you. Where's the minus sign? It's right there. Conservation of energy knows. You don't have to do this weird, figure out what the cold and the hot sides are, right? It's just, you just write down conservation of energy. You add it up to 0, you're done, okay? The math here, little bit of kind of weird algebra to get this out by itself, right? But it's just whatever this number is and this number moved over to the other side, okay? And then the numbers over here divided into whatever I don't want to do it. I got 438. And then the standard units would be joules divided by kilogram You can do Kelvin or degrees Celsius. I don't care because they're the same for calorimetry. Okay, that 438 is about iron. Okay, iron is 448, so we're kind of close enough. Right. This is the lab that we will do the Wednesday we get back from Thanksgiving vacation. Our final lab. Well, now that I say that, maybe not. Well, I hate this lab, so what?
Do projectile motion instead.
No, we're not going to do projectile motion. I'll think about it. We may not do it. We might just review for the exam instead.
Will you put the chart of all of
I will always give you, unless I'm asking you to find a specific heat, I'll give you all the specific heats you need to know. It's one of those like table things that I would just give you that. You could just ask me during the exam, I'd just give it to you.
So if we're finding the specific heat of something, I know like in chem,
Mm-hmm.
you're finding it, then you like look at the table and like match like what it
What it would be? Sure.
like would that be the kind of question, or would it just
Nah, I'd probably just ask you to find the number. Yeah. Physicists are less interested in what it is. Chemists always are picky about that. So just for those of you, how many of you have had chemistry before? Have done this in chemistry? Yeah, like quite a few of you. And some of you aren't raising your hand. It's okay. You're fine. Just follow this. You'll be good. Okay? For the rest of you that have been corrupted by chemists, understand, right, that this is different from the way you learned it the first time, right? Okay? And so there can be confusion there, right? It could be very confusing in your mind. If you want to fall back on the chemistry way of doing it, I can read that no problem. I will not mark you down for doing it the chemistry way. Okay? If that's what you're comfortable with and you want to figure out what the cold thing is and blah, 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 by all means, right? Whatever you do, don't mix the methods. Don't use Q hot equals Q cold and then ignore the temperatures that are in that. So for those of you who had chemistry, let me just show you how bad it is. This is what chemists do. They'll do Q hot equals negative Q cold. And over here, you have an MC delta T, that's the normal delta T. But over here, they'll have an MC, and this will be T initial minus T final. And they really won't tell you why they did that. I don't know why. I mean, they just pulled the minus sign out and reversed this for no good reason other than, well, it's got to be cold, so it has to be giving up heat. No. Yeah, just. But I, as a teacher, will not grade you down for doing the chemistry way. I might think you're weird, but I won't grade you down. Okay? Especially because that might be the first way that you learned how to do it, right? Okay? But if you want to just do the physics way, 0 equals, and then just plug in things, right? This gets mathematically harder if they ask you to solve for T final, right? Because then you have if you're being asked to solve for T final, you'll have T final will be in all 3 of the terms. So then you just have to factor things out. My advice is get the numbers in as fast as possible. Usually I'm do it all in symbols first and then do it. No. In this stuff, put the numbers in as fast as you can. So that way it's easier to see what the unknowns are, to factor them out and keep going. So, all right. Phases of materials. We're talking about solids, liquids, gas form, okay? This is where calorimetry goes a little bit sideways because now we have to keep track of the amount of energy it takes to change the phase of a material. For example, when water is solid in its ice form and it melts, it doesn't change its temperature. The melting temperature of water is 0 degrees Celsius. And it will stay at 0 degrees Celsius until all the ice has been melted, until the entire phase change has happened. What's going on at a molecular level is that we are breaking bonds and causing more wiggles and all kinds of stuff is going on. And back in the day, before they understood about atoms and molecules, they called this latent heat. Latent is a fancy Latin word for hidden. It was the hidden heat. So when you go to cook some pasta, if you happen to read the directions on the package, which I haven't read in, I don't remember if I've ever read it. Because in my family, you just don't read directions on packages. You just are born knowing how to cook pasta. I'm Italian-Hungarian, so like pasta's our jam. I fully acknowledge that the Asians invented noodles. Perfectly okay with that. Thank you for your contributions to food history, right? My people, the Italians, perpetrated the travesty of the fork on all of society. I'm sorry. Forks are dumb, okay? Chopsticks are better. Just saying it right now, okay? Anyway, when you look at the package of pasta, what does it tell you? Like, to get your pasta cooked, what does it tell you to do? Boil some water and then put the noodles in for a certain amount of time. How do they know how much time to tell you? Well, of course they did, but what's the thing they're counting on for that time? What must be true about the water? Has to be boiling, right? Because if water is boiling, it's changing its phase. It's going from liquid to gas. As it changes its phase, what temperature is it? 100, guaranteed, unless you live in Colorado. Okay? This is why there are not very many good Italian restaurants in Denver and why Italians did not move there. Okay? The Mile High City, 5,000 something feet above sea level, right? What happens to the atmospheric pressure? Drops, which means that water boils at closer to like 94, 95 Celsius, which means the pasta has to be in the water longer to get cooked, and the longer you cook pasta, the yuckier it gets. Okay? There's this stage of pasta. This is cooking with Mr. Balogh, by the way. There's this stage of pasta called al dente. Okay? It means it's Italian for to the tooth. Okay? Meaning that when you bite into it, the pasta should have like a soft outside and then like a resistant inside. Not raw, but it should like kind of work against your tooth. That's perfect pasta. You do not tell this by throwing pasta at the wall. All that does is make the wall sticky, okay? It doesn't tell you anything about the doneness of the pasta. You can actually look. As a matter of fact, some, especially Asian pastas that are made out of rice or beans, it's harder to feel that al dente because the noodle itself is kind of soft. And so what you do is you look at the noodle and you'll know it's ready when there's like a kind of an opaque middle part and then the outside looks a little bit clearer, right? You can actually visually tell when the pasta is done. So the manufacturers of these pastas know what to tell the end user because water keeps its temperature the same temperature no matter what. And I love to think of phase changes as a staircase, right? Below 0 degrees, you can change the temperature of ice. Like you take it out of your freezer's at like negative something Celsius, I can't remember. It's like 0 degrees Fahrenheit, okay? You got to warm up the ice before it begins to melt. And so ice, water, any drink with ice in it will always have a temperature of 0 degrees Celsius because if the ice is actively melting, that's what the temperature is going to be. Unless it's the bottom of the cup, in which case it's going to be 4. All right. And then once you've melted all the ice, we start increasing the temperature again, okay, until we get to the boiling point. The thing about latent heats is that the temperature, the amount of heat that's required doesn't depend on temperature. It just depends on mass and this constant called the latent heat, okay? And it's plus or minus. The only way I can tell the difference between plus and minus, this is where you actually have to put a plus and minus in your add up to 0 thing. It's plus if you're heading up the stairs. So if you're melting water, if you're going from a lower temperature to a higher temperature, you're going up the stairs, it's plus ml. And if you're coming down, if your water is freezing, it's going to be minus ml. Unfortunately, there's lots of numbers on here, okay? So if we look at water, here's water, okay? The normal melting point is 0, okay? And here is the latent heat for this part of the stair step. There is a different constant at 100 degrees. There is a different constant for this stair step. Vaporization is this top step up here. Fusion is the bottom step. So when you go and you look up these things, whether it's on Google or on the screen or your book, latent heat of fusion is the number that is used if you're going from solid to liquid or liquid to solid. The direction of that is just your plus or your minus sign. Vaporization, the latent heat of vaporization, which would be this number right here, is the number, the constant that you use if you're going from liquid to gas or gas to liquid. And what determines the sign? Which direction you're going. You're going up the stairs or down the stairs. So generally when I solve one of these problems, I will really quickly just draw this shape, right? Okay? And I'll just kind of orient myself, like what's going on in the problem. I run out of time to do an example of this. I'll do this example on Thursday. But we're still going to just add all of our changes in heat up to 0. We're just going to be careful about doing it when we have a phase change that is taking place. I'll see you tomorrow for, I'll do this tomorrow. Whee! Okay? As I finish out, I'll finish chapter 12 and 13 tomorrow. This is what I'll do.
What about sublimation and deposition?
We don't worry about it.
Oh.
Yeah.
But